Hello everyone, and then welcome to another video. Okay, so in this video we'll be treating the second law of thermodynamics. Okay, right, so let me get this out of the way. Second law of thermodynamics is most of the time entropy based. Okay, it means that we normally talk about entropy. Okay, right, so let's take a look at some of the basic concepts and then formulas, and then we dive into solving some questions so that you get to understand the main concept of what second law of thermodynamics. In case you are new to this channel and then you might benefit from this tutorial video, kindly consider subscribing to the channel. Okay, hit on the bell icon so that you don't miss out on any uploaded video. Like the video, share, and then let me know your comments. Okay, in case you have any questions, you just leave them in the comment section and then I'll reply to them as soon as possible. Okay, right, so first let's look at enthalpy. Okay, so enthalpy is all about disorderness of a system. Okay, whenever there is disorderness in a system, okay, and then we have the formula for enthalpy to what H is the enthalpy. Okay, and then we have E, that's the internal energy. Okay, and then we have the pressure in the volume. So you could take the change in enthalpy, change in internal energy, and then change in the PV. Okay, and then for two states, okay, you can just write the PV into split them into two. That for two states we have P2 V2, and then we have minus P1 and V1. That's the change in PV. Now it could also be work done. Okay, right, so we know that from first law of from ideal law, we know that PV is equal to nRT. Okay, and then since PV is equal to nRT, we can just substitute PV with nRT so that we get change in nRT. Okay, this is quite simple and straightforward. Now let's proceed, and then we know that change in E is equal to the change in U. Okay, now let's proceed towards the most important concepts. Okay, so now entropy for an ideal gas is equal to the final entropy subtracted from the initial entropy. Okay, now take a good look at this equation. Is very important. Okay, this is where you have two states. Okay, so from state 1 to state 2. Okay, state 1 to state 2. So we have the Q, that's the energy, okay, divided by the temperature. Okay, so for two states you could have just like integrals. Okay, so you could have for the first state and then subtracting from the second state. Okay, keep that in mind, it's very important. Okay, right, so entropy actually could be written in different formats. Okay, depending on the parameters which have been made available in the question. Okay, right, so for entropy, S2 minus X1, you could get that straight ahead. Okay, you could get that straight for it. That's why you are given entropy 1, entropy 2, and you are told to find out the change in entropy. Or you could be given maybe the number of moles, the CV, and then maybe the change in temperature, and then maybe change in volume, and then you'll be told to find the entropy. Okay, right, so or we also know that number of moles is equal to mass of molar mass. Okay, so sometimes we might be given the molar mass and then maybe the mass, and then you will be required to find the moles and then substitute the moles into this equation. Okay, so entropy is dynamic. Okay, it depends on the parameters which have been given, okay, which have been made available to you. Okay, now let's look at this formula too. Okay, so this formula means that we've been given the entropy in the form of logarithm. Okay, so from here we were given in the form of lane. Okay, and then it was CV. Okay, but here you could notice that we have R. Okay, there's no CV no more. Okay, right, so R, so we have R over here, R over here. So this you could this is how you could write entropy. Okay, in terms of the R. Okay, as 8.314. okay, something like that. Right, so let's proceed now. For P and T as variables, okay, so for states, okay, we have what? P1 V1 divided by what? T1. So note that we could have what? PV over T, okay? Right, so this where you have only one state, okay? But this where you have what? Two states, okay? Right, and then we have what? Ideal equation again, okay? PV equals what? nRT. But here we have what? The V in what? Two states, okay? Right. So that's where we have this equation, and then from here we have, okay, this equation, okay? Some of these equations are what? Substitutions. Sometimes you might need them to do what? Substitutions, okay? So keep some of these equations in mind, okay? Now, since we know that Cv plus R, okay, the gas constant is equal to what? Cp. This is what? Cp. Then we could also write entropy in this form, okay? You could also write entropy in this form. That's why I stated that second law is all about entropy, and then the question, okay, will require you to use certain equations, okay, that you need to keep in mind, and then you have to know which equations to use, okay? Right. And then you need to keep these three in mind, okay? Isothermal means what? Constant temperature. Isobaric means what? Constant pressure. And then isochoric means what? Constant volume. Again, you could notice that entropy could be also represented in this form, okay? All the formulas which have been circled with specific colors have to be what? Be kept in mind, okay? It's very important. They are very crucial, okay? Right, so let's dive right into what? Solving some questions, and then we'll call that what? A day, okay? Right, so let's look at some questions, okay? Right, so we are to what? We have given what? A reversible heat engine receives what? 3,000 kilojoules of heat, okay? Receives heat engine of 3,000 kilojoules of heat from a constant temperature, okay? So constant temperature, it means that what? Isothermal. Okay, so isothermal means what? Constant temperature at what? 650 Kelvin, and then if the surrounding is at what? 295 Kelvin, determine what? Availability of heat, and then what? Unavailability or unavailable what? Heat. Okay, so let's look at how we solve this question, okay? Okay, so we've been given heat at what? 3,000 kilojoules, temperature T1 at what? 650, and then what? T2 as what? 295. Okay, so we have to find what? Availability of what? Heat energy, and then what? Unavailability of heat energy. Now, so from here, you notice that I quoted a specific equation, okay, which was in this format, okay? Right, so we have the heat, okay, and then divided by what? Change in temperature. That's why I said that what? I stated that what? We have what? State 1 and state 2, okay? Right, so that's the entropy. Now, let's see how we go by this, okay? Now, so from here, you can just split this one out, and then we have what? This energy, okay? This heat energy will be equal to what? This entropy will be equal to what? The heat energy divided by what? The two temperatures, okay? So you could either be what? T2 minus T1, or let's say maybe T1 minus what? T0, okay? Right, and then we have what? 3,000, okay? Divided by what? The change in what? The temperature, so we have what? 650, okay? But notice that for here, we are adding, okay? There is no subtraction, because this is not two states, okay? In case temperature and two heat engines, okay, with different heat energies, we could have done that with what? Two states, but this one we have only one heat what? Energy given, okay? So we have what? 295, okay? And that will give us what? When you compute this, you end up with what? 3.17, okay? 3.17 kilojoules per what? Kelvin, because this is what? In kilojoules, and then the whole of this, okay, is in Kelvin, okay? Now let's look at what? availability of heat, okay, now, or available heat, okay. So available or availability of heat, okay, is equal to what? A to be equal to Q. Okay, so for availability of heat, all we are trying to do is what? Just multiply what? Temperature by the entropy, okay? By the change in entropy, because we've already calculated change in entropy over here, okay? So this is a change in entropy value, okay? Right, 3, okay, let me rewrite that. Okay, we already know what change in entropy, okay? So now we are just finding what availability of heat. So is what this Q, okay, and then we subtract that from what change in entropy multiplied by what the temperature, okay, right? And then note that this is what T naught, okay? So we have what Q value, which is what 3000, okay, and then minus what T naught, okay? We know T naught to what 295, okay, 295, and then you multiply that by what entropy, okay? So that's what 3.17. One thing I didn't even mention is that whenever you are working with thermodynamics, kindly take note of the unit, okay? The units are very, very important. They are even important than the value you get for your answer, okay? Very, very important. So when you compute this, you end up with what 2064, okay, 0.85, okay, and then the unit is what? This is what heat, okay, so it's what kilojoules, okay, right? And then let's look at what unavailable heat, okay? So for unavailable heat, so we have this A and this B. So unavailable heat, okay, it means that the heat which wasn't available, okay, unavailable heat, okay. Now unavailable heat is equal to what U minus A, okay. That is what the unavailable heat, okay. So that is also equal to T naught multiplied by what change in what entropy, okay. So when you compute that, you end up with what 295, okay, then multiply by what entropy, that's what 3.15, and then that will give us what 935.15. This is also heat, okay. So we have what kilojoules, okay, right? So this is quite simple. Now let's dive right into the second question, okay, right? So this was quite simple and straightforward. Now let's look at something a bit complex, okay, right? So let's see, we have what air in a closed vessel of what fixed volume of what 0.15 meters cube exerts pressure of what 12 bar at 250 degrees Celsius, okay. If the vessel is what cooled, this is what cooled is cooled, okay, so that pressure falls to 3.5 bar, determine what the final pressure, okay. So we've been given initial pressure over here, we have defined final pressure, we've been given initial temperature, find heat or transfer, and then what entropy. Now let's see how we solve this question, okay. So we've been given what our parameters. We have V1 to what 0.15 meters cube, okay, and then we have pressure 1, okay, to what 12 bar, okay, which is also equal to what 1200 what kilonewtons, okay, per meter squared. Because of this unit, we want the units to be what the same, and then we have what pressure 2, okay. Pressure 2 is equal to what 3.5, okay, 3.5 bar, okay, 3.5 bar, okay. Then 3.5 bar, when you convert 3.5 bar, you end up with what 350, okay, kilonewton divided by what? Meters squared, okay. And then we have what? Temperature, okay, to be equal to what? 250 degrees Celsius. And then when you convert that, you end up with what? A certain 273 plus what? 250, okay, and that will give you what? 523 what? Kelvin, okay. Now, since we know all of this, let's look at what? How to find our final pressure, okay. Right, so you know that from ideal gas law, okay, from ideal gas law, you know that PV is equal to nRT, okay. And then from here, you know that this is the same as what? PV is equal to what? Mass over what? Molar mass RT, okay. Now, let's say RT and then molar mass are constant, okay. Let's say they are constant, and then we are finding what? Mass, okay. Let's say we are finding mass, okay. So mass will be equal to what? PV, okay, divided by what? RT, okay. So we've been given P1, so let's say this is P1, we've been given V1, and I'm giving what? T1, okay. R is what? Constant, okay. So now all you have to do is just insert your values, and then you end up with what? Your M, okay. So this M will be used in this formula, okay. This formula, okay. This formula, okay, is very, very important, okay. Now let's proceed, okay. Right, so we have M, so we can now calculate for what? M, since we know P1, V1, and then T1, okay. So we have P1 to what? 1002, and then you multiply that by what? V1, okay, that is what? 0.15 divided by what? 8 R, okay. So R in this context, okay, is equal to what? 0.287, okay, per the unit, okay. There's our R, and then we know our temperature to be what? 523. So now our M value to be equal to what? 1.2 kilogram, okay. Very, very important, okay. 1.2 kilogram, okay. 1.2 kilogram. Now we are now about to find out final pressure, okay. So now let's see, we know M, okay. So now final pressure, so for final pressure we have what? From final pressure we know that T2, okay, T2 has to be equal to what? T1, and then you multiply that by what? P2, P1. So from our initial stages we learned something about what? Charles' law, Boyle's law, and all that, okay. So from there you can notice that there is another law, okay. Right, so and then we are looking for what? Final pressure, okay. Right, so from here you can notice that we could calculate for what? T2, okay. So for T2 we know that what? Our T1 is what? 523, okay, multiplying P2, okay, which is 3.5, and then divided by P1, which is what? 12, okay. So when you compute this, you end up with what? 152, okay, 0.54, okay, Kelvin, okay. So these are what? T2, okay. Right, so let's move on to what? The heat transfer, okay. So this is what? This is supposed to be what? Final temperature, okay. Pardon for that, because we've been already given what? The final pressure, okay. So this is final temperature rather, okay. This is final temperature as we've been able to calculate over here, okay. So now let's look at B. we are finding what? Heat transfer, okay? So heat transfer, for heat transfer we have what? Q, okay, is equal to mCp, okay, and then we have what? Change in what? Temperatures, okay? Right, so this is how we find out what? Heat transfer. So we know M, okay, we know M to what? 1.2, okay, that's from here. And then we know what? Cp, okay, so Cp is something like a constant, okay? Cp most of the times constant, okay? So it's giving us what? 1.005. So most of the time it's being represented as what? 1, okay? Cp, because 1.005 is approximately is equal to what? 1. And then we have our T2, okay? We have T2 to what? We have T2 over here, so we have what? 152.5, and then we already know what? Our T1, okay? T1 is what? 523, okay? So let's see what we will get for what? Our Q value. So this is our Q value. That's a heat transfer, okay? So when you compute this, you notice that from here, from this computation, you can notice that we end up with what? A negative value, okay? So we have minus 446, okay, 0.78 kilojoules, okay? Right, so this negative sign means that, okay, means that heat is being rejected from the system, okay? The heat is being rejected from the system, okay? That's what the negative sign means. Heat rejected from system, heat rejected, okay? Heat is being rejected from the system, okay? So now let's take a look at our final calculation. That's what? Change in entropy, okay? So C is what? Change in entropy, okay? So for change in entropy, that's why we calculated our M. So change in entropy is equal to what? M, okay? And then we have what? Cp, okay? Cp ln what? T2 on what? T1, okay? And then minus what? R value, okay? And then we have what? Ln of what? P2 on what? P1, okay? Just as I showed you over here, okay? Right, so I showed you this formula, okay? Or I introduced this formula to you, okay? Not too long ago, okay? Right, this formula is very, very important. So that's what we are trying to implement, okay? Right, so we have our formula over here, okay? Right, so let's proceed by what? Inserting our values, okay? Let's proceed by our values, okay? So we have our values to do what? We know M value. M is what? 1.2, and then you open a bigger bracket, and then we have a Cp. Cp is what? 1.005, just like here, okay? And then we have what? Ln of what? T2. You know T2 to be what? 152.5, okay? Divided by what? T1, which is what? 523, okay? And then we subtract that from what? Let me put this in bracket, and we subtract that from what? R. So R value initially was what? 0.28, right? 287, okay? 287. Then let's take the ln of what? P2, okay? We know P2 to be what? 3.5, and then P1 to what? 12, okay? Right, so once you compute all of this, once you punch all of this on your calculator, you end up with what? Your change in entropy value, okay? Change in entropy value to be equal to what? 1.06, okay? Kilojoules per what? Kelvin, okay? Take note of the units in what? Thermodynamics. Very important. Okay, right. So thanks a lot for staying with me to the end of this video. Kindly subscribe, hit on the bell icon so that you don't miss out on any uploaded video, and then I will see you in the next video.